In this lecture, we will take up asynchronous counter using JK flip-flop. Now, what is the basic of an asynchronous counter? It is basically known as a ripple counter. In this counter, the output of one of the flip-flop drives the clock of the next flip-flop. So, in this type of arrangement, the flip-flops for constructing counters are usually called asynchronous counter, and as not all the flip-flops work in synchronism with the applied clock, so the clock is applied to the least significant flip-flop, and the output of that particular flip-flop drives the next flip-flop, and the next flip-flop's output drives the next flip-flop. So in this case, in this order, the information is passed on from one flip-flop to another flip-flop and another flip-flop to another flip-flop. Hence, we actually call it a ripple counter. Now, what we will be discussing today is a simple 3-bit asynchronous up counter using JK flip-flop. Now, let us consider a very simple 3-bit asynchronous counter, and we'll be considering negative edge triggered JK flip-flop. Now, in this flip-flop, we'll be also having preset inputs, clear inputs, and those asynchronous clear inputs will be used to momentarily clear the output of the flip-flops. Now, whenever we use the flip-flops, the output of the flip-flops are always unpredictable when they are first switched on. So it is always prefer to start the counter from a predefined value. In this case, we'll be clearing all the outputs of the flip-flops so that it starts from 0. Now, since we are not going to use the preset inputs, we are actually going to disable them. So in order to disable any of the asynchronous inputs like preset or clear, what we have to do is we have to pull it to high logic. Since the inputs are active low type, that means if we connect the preset or clear inputs to the ground, they get activated, hence they are active low type. So in order to disable them, what we have to do is we have to connect them to higher logic. Now again, there is another thing that we call is the mode of the counter. So the number of states that the counter shows is actually the mode of the counter, and it is usually given by 2 to the power n, where n is the number of flip-flops. Now, all the G&K input of the flip-flops will be connected to logical high so that the G&K flip-flops actually work as a toggle flip-flop. Now, the output of the first flip-flop will act as the clock for the next one, and so on. So, to provide the clock at the initial or the first flip-flop, we can either use signal generators, clock generators, or we can use cross-coupled NAND gate, which are actually also known as debouncer circuits, to provide a manual clock to the counters. All the inputs of the cross-coupled NAND gates, which are actually going to be used as manual clock, should be tied to high logic. When the counter circuit is powered first time, the output of the counter will be arbitrary. So in order to start, again I am repeating this, in order to start the counter from a predefined value, we can either use preset or clear, but in this case we will be starting the counter from 0. So what we will do is we will tie all the clear inputs together and momentarily connect that to low logic. Now we have to remember one thing, these are asynchronous inputs. So if we have connected all the clear inputs and connected them to the logic low, the counter will not respond until and unless we disable those clear inputs. So even if there are some clock inputs or inputs to an JK terminal, the output will not change until and unless we remove the clear terminal from low logic. So once we have cleared the output of the flip-flops, that is we are resetting them to 0, we have to remove the signal from the clear inputs. So if we look into the frequency division part of the counter, we can see that in this basic counter, where we use flip-flops provide an output waveform that is exactly half the frequency of the waveform at its clock input. That means suppose in this particular diagram we can see a JK flip-flop. Here it is a negative edge triggered flip-flop, so a clock has been applied to the clock input, and since both J and K are connected to high, it's going to toggle. So let us first assume that the output was 0. So what we will get a high output for the first clock, then the output will toggle to low and the next clock, and on the very next clock it will again toggle back to high. So this will keep on happening until it goes on, till the clock is applied. Now the complementary waveform will be available at Q bar. So here we can see one thing is, see, uh, the the clock frequency of the clock frequency, if it is F, we can see it has just got half in case of the output at either Q or Q bar. Now let us try and understand the circuit. Since we are using 3-bit, so we'll be considering 3 flip-flops. All the J and K inputs are connected to logic high, and all the clear inputs are connected together. The presets will be connected to logic high, so that we will not be using the asynchronous preset inputs. We are going to use the clear only for a moment when we need to clear the outputs. Now this is a manual clock, which is otherwise also known as debouncer circuit, usually constructed out of cross-coupled NAND gate. The inputs of the cross-coupled NAND gate should be tied to +5, and we will have a wire connected to ground, and if we switch back from the S to R, we will be able to get a manual clock at the output. Now that manual clock will be first applied to the least significant flip-flop, which acts as the least significant output, that is the LSB output of the counter, and the output of that will get connected to the next clock input of the flip-flop, and the output QB is then again connected to the clock input of the next flip-flop. So in this case, QC is the most significant bit and QA is the least significant bit. Now if we have to clear the outputs QA, QB, QC, we will have to connect the clear input momentarily to the ground, as shown by the dashed line. Once it has been cleared, it has to be opened and connected to the high logic, so that false clearing never happens during the operation of the counter and the clear inputs get disabled. Now let us consider a clock input. There are 10 edges we can see. This is the first negative edge, this is the second negative edge. So when the first negative edge appears at the clock input of the first flip-flop, if we consider the initial state to be 0, as we have already cleared the output, it will get back to high, and in the next clock edge it will get back to low. Since we are considering this as a toggle flip-flop, it will keep on toggling between 1 and 0 for respective clock edges. So we can consider this waveform where upon reaching the first edge, the QA toggles to 1. On reaching the second edge, the high goes to 0. Again on the third edge, it goes to high, and so on. Now this behaves as the output for the next flip-flop. So we will mark all the negative edges of the QA output, and then again we will assume QB to be 0 till it receives the first negative edge. So this is the first negative edge that is received by QB flip-flop, that is the second flip-flop, and it was 0 and it toggles to 1 and so on. Similarly, we have to mark all the negative edges of QB, and we have to now consider the output of QC. Now we can see the output of QC will toggle at the first negative edge, and again it will toggle at the next negative edge. We have to check one thing. This is not the negative edge, it is actually the positive edge, and again this one is not the negative edge, this is the positive edge. So the listeners are requested to ignore this too. We are only considering the falling edge of the clock. So the output of the last flip-flop will respond to the falling edge of the QB output, and similarly the next toggling of the output will happen on the next falling edge of QB. Now if we consider the outputs, we can see before the first edge we have all the outputs as 0. Between the first and second we have 0 0 1, this is high. The next is 0 1 0. Between 2 and 3, the next is 1 1 0. So you can see the counter is counting. It's from 0, it has now become 1, it has now become 2, it has now become 3, similarly 4, now it's 5, now it's 6, now it's 7. Once it reaches between 7 and 8, the output is now all high, and the counter will automatically reset back to 0, and again it will start counting. So this is how a simple ripple 3-bit counter functions, where one of the output behaves as the clock for the next one, and the output of the next one behaves as the output for the third one. So in this case, none of the flip-flops work together. Only the first flip-flop receives the clock. The clock can be provided by a manual trigger or by a clock generator, and the information propagates from the first flip-flop to the next, and from the next to the next. I hope you have understood this particular concept of a 3-bit asynchronous counter, and I thank you for watching the video. Thank you very much.